Hello everyone, and welcome to Natural Resources Canada's e-training module on using meter data to improve energy and water efficiency. This course has been adapted from the U.S. Department of Energy's Federal Energy Management Program training material on meter data for energy and water efficiency. This training is being delivered through the Natural Resources Canada Greening Government Services to help federal departments and agencies plan and implement projects that reduce the energy use and greenhouse gas emissions of their buildings, laboratories, other facilities, and vehicle fleets. Over the years, Natural Resources Canada has been successfully developing comprehensive methodologies, practices, and tools to reduce energy consumption and greenhouse gas emissions for the private and public sectors, including the federal government. Since 1991, NRCan has provided enhanced technical support to Government of Canada organizations seeking ambitious greenhouse gas emission reduction actions from their building and fleet operations. This training will support federal organizations to meet their commitments and lead by example. The federal government has committed to reducing emissions from their operations by 40% below 2005 levels by 2030 and by 80% by 2050, as outlined in the Greening Government Strategy. It is important to note that federal buildings represent almost 90% of the government's greenhouse gas emissions. This initiative also supports the commitment by Canada's federal, provincial, and territorial First Ministers to scale up efforts to transition to highly efficient buildings and zero-emission vehicle fleets, as specified in the Pan-Canadian Framework on Clean Growth and Climate Change. This course will discuss how metered energy data can be analyzed and presented to support effective decision-making. After taking the training, you will be able to use metered data analysis to improve operational efficiency, understand basic concepts related to building load profiles, and apply metered data to identify water conservation opportunities and analyze utility bills. To meet these learning objectives, this course is divided into 5 sections that reflect the process for applying metered data to improve energy and water efficiency. Each section will open with an introduction and conclude with takeaways. First, we will discuss how metered data analysis is used to inform decision-making and improve operational efficiencies. Next, we will discuss the basics of load profiles and how they can be used to make key energy decisions. Then, we will examine how to use metered data to identify water management opportunities. And finally, we will discuss how to analyze utility bills to verify metered data. The course will conclude with a short quiz to assess your knowledge of the material. To begin, we define some common terms used in this course, including load profile, peak load, base load, and occupied/unoccupied hours. A load profile is a graphical presentation of energy use versus time, typically looking at the daily, weekly, or monthly interval loads. On a load profile graph, the x-axis has time and the y-axis has average energy use. For each time interval, the energy or water use is presented. In this example, each interval is 15 minutes in duration, and the energy use presented is the weekday average in kilowatt hours. The next term is peak load. Peak load is the load period when energy and water use are at their highest levels. Peak load values should be reviewed for the time of day they occur, magnitude, and duration. The graph is of a load profile, with time on the x-axis and average energy use on the y-axis. The peak load is where the graph is at its highest on the y-axis, which is around noon, where energy use goes to almost 120 kilowatt hours. Next is base load. Base load corresponds to the energy use that occurs 24 hours per day. The base load energy use occurs during both occupied and unoccupied periods, and usually consists of security lighting, ventilation, and continuously operated plug loads. Base load values should be reviewed for the time of day they occur, magnitude, and duration. Typically, building energy use during unoccupied periods should be 20 to 30% of the building's peak load. If energy and water use are not as expected, look for performance improvement opportunities. The graph provided is of a load profile with the base load identified by the yellow dotted line, illustrating the base energy use of around 25 kilowatt hours across the 24-hour period. The final key terms are occupied and unoccupied hours. Occupied/unoccupied hours are used to describe a building's operational state. During occupied periods, the building systems and occupant plug loads are in use. During unoccupied periods, building energy use systems should be shut down or set back. The occupied and unoccupied periods for a building should be reflected in the building's operating schedule and equipment startup and shutdown schedules. Most federal office buildings follow a Monday through Friday schedule where occupancy begins around 6 or 7 a.m. and ends around 6 p.m. These office buildings are also typically unoccupied on weekends and holidays. The load profile in the graphs illustrates that energy usage spikes around 6 a.m. and declines sharply around 6 p.m. Therefore, the occupied period is between 6 a.m. and 6 p.m., and the unoccupied hours are from 6 p.m. to 6 a.m. Now let's briefly discuss how to use data analysis to inform decision-making. Meter data analysis is a valuable tool for informed decision-making. The first step is to select a building or set of buildings for analysis. Ideally, select buildings that have good operational knowledge and quality meter data. Operational knowledge includes familiarity with the building's function and design, an understanding of the building's regular occupancy, and a record of events that may have impacted energy or water use. Let's outline the steps required to conduct analysis of meter data. Once a building or set of buildings have been selected for analysis, undertake a high-level whole building analysis to determine if data appears logical. To do so, review the monthly total energy use for predictable variability between the seasons, such as higher energy use in the summer months to support air conditioning. Compare monthly energy use data against the previous year's data for variability or similarities. Next, use the meter data to identify base and peak loads. Finally, review the operating schedule to confirm building systems are operating as intended. These high-level analyses serve as a basis for tracking building performance over time and can be useful for identifying potential issues, anomalies, or operational questions that may warrant further review. To recap what we've learned so far, analysis of meter data begins with a high-level review of whole building data. A building's load profile is a helpful tool in identifying energy use patterns, including the peak and base load. These patterns can be used to determine if the building's operation reflects its occupancy schedule and to identify potential efficiency opportunities. The next section will discuss how to use meter data to improve operational efficiency, starting with the data needs of various data users. Data users at the department, campus, and building level have different energy data analysis needs. For example, department-level data users use annual data to set and track energy goals and report on energy use and cost trends. Campus-level data users use monthly data to track goals, analyze energy use and cost trends, and benchmark buildings. Building-level data users use interval data for these tasks, as well as to create load profiles that identify efficiency improvement opportunities. Meter data can be used in many ways for management reporting. Some key terms for management reporting are time series data, total energy or water consumption data, annual energy consumption data, and energy or water use intensity. Each of these terms is described in turn. Time series data shows all data points recorded during a specific time period. Time series data can be used to check the quality of the metered data as well as to determine if operational changes had the expected impact on energy use. Total energy and water consumption data can be examined monthly to compare performance with utility bill data. If the meter data does not match the utility data, the analyst can examine whether the meter is functioning properly and/or follow up with the utility to address potential billing issues. The graph shows total energy consumption for various buildings over many months. To continue, here are two more key terms for management reporting. Annual energy consumption data can be used to develop utility budget forecasts, compare performance between buildings, or compare current building performance to past years. Energy use intensity, or EUI, and water use intensity, WUI, are common metrics to benchmark performance towards federal energy and water efficiency goals. EUI is frequently used to compare performance of similar building types. Energy is reported in kilowatt hours per square meter per year. Water is reported in liters per square meter per year. The graph shows energy intensity levels for various buildings over many years. Next, we will briefly discuss the purpose of metered data. The primary purpose of metering is to collect and analyze data to improve operations. While meters provide data, data alone does not constitute information or knowledge. Data must be processed and analyzed in order to generate information. Information, in turn, informs actions that reduce energy and water consumption and avoid costs. Advanced and super users can use building load profiles to identify specific operational improvements that reduce energy and water use while providing necessary services for building occupants. To summarize this section, meter data can be used to benchmark building performance and identify operational efficiency improvements. Department data users use meter data to set and track goals and observe energy use and cost trends. Campus data users use meter data to track goals, trend the energy use and cost, and benchmark their buildings. Building data users use meter data to identify energy efficiency improvement measures in addition to the uses of the campus data users. The type of data gathered and data analysis should be tailored to meet the needs and capability level of its user. Next, we will look at load profiles, which can be a powerful data analysis tool. This section will discuss how to read load profiles and use them to improve energy and water efficiency. Let's begin with how to read load profiles, starting with a weekday load profile. This graph shows a weekday electricity load profile for a typical federal office building. The x-axis shows 24 one-hour time increments beginning at midnight. The y-axis shows the average electricity use in kilowatts. A load profile's 24-hour period can display either direct readings for a particular day or an average for multiple days over a period of time, such as one work week or 5 24-hour periods. As displayed by the load profile, electricity use for this building hovers around 65 kilowatts during nighttime hours. This baseline energy use appears to be higher than it should be. Building startup usually occurs around 5:30 a.m. System startup times are typically in advance of the building's scheduled occupancy. This is done to provide acceptable conditions for occupants upon arrival. Building operation continues to ramp up as different HVAC, lighting, and plug load systems engage until about 8 a.m. when energy use begins to level off. The building load remains fairly level during business hours, averaging between 115 and 125 kilowatts. Around 4 p.m., electricity load tapers off as occupants begin to leave for the day and energy use declines. Energy use continues to ramp downward until 10 p.m. when the unoccupied baseload of about 65 kilowatts is reached. Now let's compare weekday and weekend load profiles. The load profile on the slide shows the average electricity load for an office building on weekdays and weekends. The x-axis represents time from midnight to midnight, and the y-axis represents the metered electricity use in kilowatts taken from the meter's recorded interval data. The blue line depicts the average weekday profile. The orange line shows average load on Saturday. The green line represents the average load on Sunday. The difference between the weekday and weekend profiles indicates that this building is normally occupied on weekdays. On both Saturday and Sunday, there is a modest increase in the electricity use that occurs around 7 a.m., indicating some activity in the building. The average load is about 80 kilowatts on Saturday and 75 kilowatts on Sunday. The electricity load decreases slowly on both days beginning at 4 p.m. and attains base load usage at 11 p.m. Now that we know how to read load profiles, we can use them to help improve energy and water efficiency. Load profiles can be used to determine opportunities to reduce load with scheduling improvements. Let's use an example with a weekday load profile. This weekday load profile shows that efficiency improvement opportunities are possible by adjusting the operating schedule. This profile reflects actions implemented to tighten the startup and shutdown profiles in the occupancy schedule using the Building Automation System, or BAS. Ramp-up start time was moved from 5:30 to 7 a.m., and the shutdown was initiated at 6 p.m. The area between the two profiles reflects achieved efficiency gains. While the electricity load magnitudes have not changed, the tightened schedules have reduced daily energy use. Building startup time now better corresponds with actual occupancy. To further reduce daily energy use, building night setback can be initiated prior to the scheduled occupant exit. HVAC systems can be turned down or off early to allow the building to float or coast, depending on occupancy, outside air conditions, and building type. Load profiles can also be used to reduce base load. Again, we use a weekday load profile as an example. In this building load profile, improvements have reduced the daily energy base load. The original pre-improvement load profile is denoted by the blue dashed line. This indicates a relatively high base load that equals approximately 50% of total demand. In contrast, a commercial office building's base load typically ranges from 20 to 30% of total demand. A base load higher than this range indicates excessive off-hour loads and should be investigated for efficiency opportunities. Strategies to reduce the base load include installing occupancy sensors to reduce electric lighting and plug loads left on during unoccupied times, recommissioning or retuning the HVAC control system to correct scheduling and set point issues, and initiating an employee efficiency campaign to engage occupants in energy-efficient behavior. These strategies target baseload energy use as well as occupied and peak energy use. In this example, these types of strategies cut baseload energy use from 65 to 25 kilowatts, putting it within the target 20 to 30% range. Load profiles can also be used to estimate energy savings after a retrofit project has been completed on a building. This load profile depicts post-retrofit energy use. Original weekday and weekend load profiles are represented by the dashed lines. Post-retrofit weekday and weekend profiles are represented by the solid lines. As you can see, retrofit activities significantly reduced weekday and weekend energy loads. The weekend base load decreased from approximately 250 to 100 kilowatts. Peak energy load has also been reduced from approximately 500 to 450 kilowatts. We can also learn from load profiles that base loads can vary widely from building to building. This graph shows average weekday electricity use of 17 individual office buildings in the month of April. Because each building has its own unique base and occupied load, the y-axis is the percentage of the occupied period average load. For example, at 2 a.m., Building 6 uses 20% of its average occupied load. Among these buildings, base loads vary from below 20% to 70% of the occupied load. Based on this range, we can tell that base loads of some buildings are actively managed while others experience partial occupancy over the 24-hour period or have continuous load requirements. This variability emphasizes that maintaining baseload energy use requires building managers and occupants' attention. For many buildings, base loads in the 20 to 30% range of the average occupied load are realistic. Here is an example of how load profiles for one day, 24 hours, can be used to verify energy savings from a retrofit project. Load profiles can be used to verify savings from energy retrofit projects like the controls upgrade represented in this image. The graph compares the before and after load profiles of a 4,000 square meter, 4-story office building that uses an HVAC system consisting of 2 roof-mounted 40-ton packaged variable air volume units with perimeter electric resistance fan-powered VAV boxes. Following a major HVAC, lighting, and control system retrofit, the energy manager was surprised to find that the post-retrofit electric energy savings was only 10% rather than the projected 23%. The renovated building's load profile indicated that unoccupied energy loads were higher than expected. Based on this information and her experience, the energy manager suggested that the HVAC fan system was operating 24 hours per day. One component of the retrofit was to upgrade the pneumatic controls to a direct digital control or DDC system. The energy manager contacted the property manager and HVAC controls contractor. Together, they determined that the final transfer scheduling to the DDC system had been overlooked. The team resolved the problem in under an hour and realized the project's anticipated savings. The energy use of individual building systems and equipment can be reviewed together using end-use load analysis. This type of analysis can identify systems and equipment that are operating out of hours and lead to reductions in a building's overall base load. To perform an end-use load analysis when submetering data is not available, start with a survey of the facility's system loads. The survey should include the nominal power ratings of equipment, including exterior lights, interior lights, HVAC system components such as fans, pumps, compressors, and cooling towers, hot water, and plug loads from equipment such as computers, copiers, and printers. Once this information has been gathered, overlay the compiled estimate for each end use onto a building's load profile. In this chart, load profiles for daytime equipment and daytime lighting and HVAC fans and pumps are aggregated to equal the building's load profile. Profiles for exterior lights and nighttime equipment are also included. This comparison identifies what equipment is operating during occupied and unoccupied hours and estimates associated energy use relative to the building load. Additional investigation can be undertaken based on the difference between expected and actual load profiles. For instance, a night walk through the building can identify equipment that is operating unnecessarily after hours. To finish this section on load profiles, let's review some of the key points with a short quiz. Based on this demand profile, a typical federal office building operating from 7:30 a.m. to 5 p.m., select the best response for each question. Question 1. What is the building base load or off-hours demand? Question 2. When does the peak demand occur? And finally, question 3. At about what time of day does building startup begin? The answer to question 1 is 75 kilowatts. The baseline is the low load that occurs over the 24-hour operating periods. The answer to question 2 is 4 p.m. The peak demand occurs at this late afternoon time and likely a result of additional air conditioning load on a hot summer afternoon. The answer to question 3 is 5 a.m. Most buildings do start their systems before the scheduled occupancy to make sure the space is comfortable for occupant arrival. However, given that this building is not scheduled to be occupied until 7:30 a.m., the 5 a.m. startup may be an opportunity for efficiency. Looking only at the shape of the demand profile, which of these represents the optimized demand profile? Green line, red line, blue line. Select the best response for the question. The correct answer is the blue line. This profile indicates a tighter startup and shutdown operation, as well as a lower overall base load and peak demand. Review the load profiles in the figure. These profiles are for a typical federal office building that is occupied 7:30 a.m. to 5 p.m. 5 days a week. Identify the actions that a building manager should consider immediately. Select 3 correct answers from the following options. Reset the equipment startup times, reset the equipment shutdown times, reset the thermostats, conduct extensive O&M on all building systems, send out a message to occupants on energy efficiency, and make sure the controls are correctly set programmed for weekends and holidays. The following are the correct answers. Reset the equipment startup times. This is a first step toward achieving optimum building performance. Reset the equipment shutdown times. This is another first step towards achieving optimum building performance. And make sure the controls are correctly set and programmed for weekends and holidays. Make sure the equipment schedules are correct for days when the building is not scheduled to be occupied. You would like to compare the daily energy use of individual buildings on your campus to identify good candidates for building automation system recalibration. Which load profile type is best for the analysis? Select option 1 or 2. The correct answer is option 1. Use a base load variation load profile to compare the average weekly electricity use of multiple individual buildings. Option 2 is incorrect. It is a weekday load profile with base load improvements, which can be used to confirm that recent improvements have made anticipated changes to a single building's baseload energy use. You recently tightened the startup and shutdown times of your facility's major systems using its building automation system and need to verify that these changes have reduced energy use accordingly. Which is the best load profile type for the analysis? Select option 1 or option 2. Option 2 is correct. Use the weekday load profile with scheduling improvements to verify that systems are starting up and shutting down at the new times. Option 1 is incorrect. The weekday load profile can be used to chart daily energy use, but does not verify on its own whether BAS changes have reduced energy use. Now that you understand load profile basics, let's look at options for presenting load profiles. Let's start with a daily load profile. This graph displays the daily load profile for each day of the week. Each workday has the same startup and shutdown time, and daily activity peaks around the same time. Systems appear to be operating as scheduled, and off-hour baseloads are consistent in magnitude. Now let's look at a load profile for 1 month. This is a load profile calendar that displays the billing load profile for each day in a month. This presentation allows the user to quickly check and compare billing performance. A building operator can use this view to determine whether startups and shutdowns are taking place as scheduled, systems are operating as expected during unoccupied periods, schedule changes have been implemented, schedule overrides exist that need to be reset, and peak and base loads are creeping upwards. The load profile calendar is a good screening tool to identify points at which additional information is needed. Next, let's identify a spike in demand from a load profile using an example. This load profile was generated to verify energy savings for a major lighting upgrade at a municipal airport. Rather than simply verifying savings, this load profile revealed an unexpected pattern of periodic demand spikes that required adjustments to reduce peak demand energy needs. A comparison of peak day versus average weekday energy use highlighted demand peaks. Weekly and monthly profiles showed that the pattern repeated. Discussion with the airport electrician uncovered that periodic tests of the concourse emergency lighting system caused the spikes. 2 solutions were apparent. Either change the switching arrangement to switch fewer relays at one time, or test at night when the background demand is lower to avoid peak demand charges. This correction reduced peak demand by about 150 kilowatts, saving the airport $500 per month. The next example illustrates how a load profile can be used to assess how a building's systems can respond to weather changes. An outside temperature overlay can be used to show how building systems respond to weather changes on an hourly basis. The green line shows the hourly dry bulb temperature and is overlaid on the building's power use in kilowatts, represented by the blue line. This comparison can be used to determine if the HVAC economizer cycle is functioning. In this example, a jump of about 40 kilowatts at 2 p.m. corresponded to the cooling compressor coming on. Based on this information, the building manager examined the economizer control settings and discovered the outside air lockout was set at 13 degrees Celsius. Raising the lockout to allow integrated economizer operation instantly reduced mechanical cooling operation and optimized energy use. To summarize this section, let's review the key takeaways from reading load profiles. Load profiles are very powerful tools for assessing building performance. The load profile itself may not highlight areas for improvement, but considering system and equipment energy loads collectively may identify anomalies and operational efficiency opportunities. Different types of load profiles can provide different insight. An end-use analysis can determine which profile types are most useful for you. The previous sections covered how to use meter data to help improve the energy performance of buildings. We now turn to the next section of this course, which discusses how meter data analysis principles apply to water management. Let's start by looking at how water meter data can be used to detect water leaks. Whole building water meter data analysis can be used to detect leaks. In buildings where water use should be near zero or near zero during unoccupied hours, analysis of off-hour baseloads can reveal leaks in elements such as restroom fixtures, kitchen equipment, and locker room showers. Water use trends can also be used to identify efficiency improvements needed by water-intensive systems. This water use profile illustrates possible plumbing fixture leaks using data from a building-level interval pulse-type water meter profile for a 24-hour period. The figure on the left is the water use profile for a typical weekday. The figure on the right is the water use profile for the same building on a weekend day when the building was unoccupied. As you can see, water use occurs consistently during the unoccupied period over the entire 24-hour period. Using the load profile data, the building operator can identify leaks in the men's restroom fixtures. Similar to how load profiles can help identify ways to improve energy management, water consumption profiles can assist to identify opportunities to reduce water consumption. This graphic displays the average daily water consumption profiles by month from January through June. The plot indicates that there is constant water use during all unoccupied periods. The consistent baseload pattern points to equipment leaks that should be located and repaired. While this course is focused on whole building meter data analysis, sub-meter data analysis can be helpful, as in the case of water-intensive systems like heating and cooling plants. Let's look at an example. As part of its comprehensive metering plan, a large research and development campus installed a sub-meter on the cooling tower makeup of the chilled water plant. By evaluating water use data provided by the sub-meter, the energy manager noticed above-average makeup water consumption occurred during January and February. Further investigation revealed that the increase was caused by a malfunctioning makeup water valve. Identifying and repairing the malfunctioning valve efficiently using sub-metering data saved the site 40 million liters of water and $27,000 in water and wastewater charges annually. To summarize this section, let's review the key points of how to use water meter data to identify opportunities to improve water management. Analyzing water meter data can efficiently identify building water leaks and operational improvement opportunities. Identifying and resolving these issues early can reduce water use, control water and wastewater utility costs, and minimize the potential for water damage. The next and final section will describe best practices for analyzing utility bills against meter data to identify potential overcharges. To start this section, let's explain what information can be gained from analyzing utility bills. Overcharges on utility bills can result from meter malfunctions, incorrectly applied utility rate structures, incorrect use of meter constants for billing calculations, and duplicate billing. To determine whether energy and water use is billed correctly, compare the building's meter data to the utility bills. Interval meter data provides an opportunity to verify monthly utility bills. Utility bill analysis can be used to monitor charges, identify errors, and evaluate costs and usage compared to prior periods. Follow these best practices to effectively analyze your utility bill. First, be sure to verify utility meter read dates. An identical number of energy use days is required for valid comparison. Next, use a proper summation process for site-owned meters. Be sure the collected data is processed using proper meter constants, pulse rates, and interval conversions to avoid errors in monthly totals. Finally, ensure you have a detailed knowledge of the utility's rate structure when performing a cost comparison. This understanding is key to accurately determining meter data costs. That concludes the course content. This course has covered the process for applying meter data to improve energy and water efficiency. First, we discussed how meter data analysis is used to inform decision-making and then in turn operational efficiencies. Next, we discussed load profile basics and provided graphic examples of how load profiles are used to make key energy decisions. We then reviewed the benefits of applying meter data to identify water management opportunities. Finally, we discussed best practices for analyzing utility bills to verify meter data. Test your knowledge by completing a short quiz on the course material. Quiz Question 1. What level of data should be examined first in the data analysis process for trends and errors as part of a high-level whole building review? A. Daily. B. Monthly. C. Annual. D. Biannual. The correct answer is B. Monthly. Question 2. What term describes when energy and water use are at their highest levels? A. Profile load. B. Base load. C. Peak load. Or D. Interval load. The correct answer is C. Peak load. Question 3. What is a graphical presentation of energy use versus time typically presented using daily, weekly, or monthly intervals called? A. Time peak data. B. Interval data. C. Peak load. Or D. Load profile. The correct answer is D. Load profile. Question 4. Which data user group is most likely to use interval data to create load profiles that identify facility efficiency improvement opportunities. A. Department-level data users. B. Campus-level data users. C. Building-level data users. D. None of the above. Correct answer is C. Building-level data users. Question 5. Which type of data shows all data points recorded during a specific time? A. Total energy consumption data. B. Interim intensity data. C. Energy use intensity data. Or D. Time series data. The correct answer is D. Time series data. Question 6. One option for reducing energy use is to initiate building night setback prior to the scheduled occupant exit, based on occupancy, outside air conditions, and building type. A. True. B. False. The correct answer is A. True. Question 7. Which is a proven strategy for reducing a facility's baseload energy use? A. Initiating employee efficiency campaigns to engage occupants. B. Recommissioning HVAC systems to correct set point errors. C. Installing occupancy sensors to reduce electric lighting loads. D. All of the above. The correct answer is D. All of the above. Question 8. What is the typical range for a commercial office building's energy baseload? A. 10 to 15% of total demand. B. 20 to 30% of total demand. C. 35 to 40% of total demand. D. 40 to 50% of total demand. The correct answer is B. 20 to 30% of total demand. Question 9. It is recommended to use building occupancy hours as the upper limit for system run times to optimize energy use while minimizing occupant comfort complaints. A. True. B. False. The correct answer is A. True. Question 10. Which is a common cause of utility bill overages? A. Meter malfunctions. B. Incorrectly applied utility rates. C. Incorrect use of meter constants for billing calculations. Or D. All of the above. The correct answer is D. All of the above. If you have any questions about this course or are interested in other training opportunities, do not hesitate to get in contact with the Office of Energy Efficiency using the contact information provided. Our email address is nrcan.greeninggovernmentvert.rncan@canada.ca. Our website can be found at www.nrcan.gc.ca/greeninggovernment. Thank you for participating.